We always hear about complexity economics, and many of us know that a couple of eminent thinkers very long ago have told us that our economy is a complex system. But what does this really mean? That's what I want to talk about, and I want to talk about how that can help complexity economics. So the other group, the complexity economists, as you see in this article, many of them are guided by their background in physics, and they also tell us that our economy is a complex system. Now, they advocate for agent-based models, which according to them can capture that complexity in an economic system. Now, an ABM is basically a computer simulation of our world, but they are now being used for policy analysis and to teach economics. So I'm interested to see how well these agent-based models can capture that complexity. So first, I looked at how eminent thinkers define a complex economic system. I want to show you that first. Then I analyzed some ABMs. I want to show you precisely why I think they fail. Currently, they're not analyzing complexity in economics as explained by these eminent thinkers. And then I'll show you how I think ABMs can be applied in a promising way. And that involves bringing our discipline, political economy, within reach of the complexity economists working on ABMs. So first, as for the definition, I didn't want to focus on a definition from physics or the natural sciences, because I know what happens when economists become inspired by physics. So I focused on our own thinkers, and that gave me a better idea of the components in a complex economic system and the mechanisms that operate between these components. So this is Veblen, for example. Individual action makes up the institutional landscape, while it's also shaped by it. And on the other hand, individual action interacts with the materials available to humankind, causing technological evolution. And the product from this process is therefore a combination of the materials, as well as the individual's insights and appreciation for how these materials can be used. And he also calls this knowledge and preference, and prevalent habits of thought. And he says that prevalent habits of thought form a broad range of institutions, which then facilitate individual action. So we can say that Veblen refers to an individual's internal environment, to an external physical environment, and to institutions. And the one is defined in terms of the other. An insight, it doesn't just hang in the air, it's an insight of an object in the physical world. But the work of all those eminent thinkers help us to define complexity in economics as a dynamic state that results from the co-evolution of these three areas. So I want to see if ABMs are doing this. And if they're not doing this, why? All right. So some researchers, they simulate artificial life in a computer environment. And then they're interested how this artificial life compares to a biological or social system. So they don't have to model anything. They don't have to explain any theory. They use the simplest rules to build this artificial life. So on the left, the rules are cells switch on and off depending on how many of their neighboring cells are on or off. And on the right, the rules are functions interact across cells, and this is the life we see. Now, this artificial domain is the genesis of all ABMs. When someone creates an ABM for a different domain, they build rules into this artificial space to match the intended domain. And if this can't be done, the model fails. But to match the physical, mechanical domain, that is easy because rules of physics are known and they don't change. So you can model, for example, pouring liquid onto a surface or the movement of gas particles. And notice there's an analogy here. You imagine that artificial cell as water or as containing a gas particle, and you encode it with those rules. So next, a modeler can take this physical particle, call them voids. Now, voids are used to simulate the movement of animals. They can be used to simulate the movement of cars to model traffic on roads. And what you get in these situations is movement in the normal situation. So it only works in isolated worlds, in rule-intensive environments that doesn't change, or where the options chosen by these agents are so clear that they can be modeled as if they are these physical systems. So then models in virology, or I should say ABMs in virology, that's even less accurate because it uses these voids to represent humans and it uses probabilities, but it cannot account for that dynamic situation where new rules emerge as a response of being inside this pandemic. And if you move even slightly further into the economic domain, getting model results that resemble real situations as is, it just disappears. And that's because we've now entered this system based on the rules explained by eminent thinkers. And we need to make analogies based on that. But that doesn't happen. ABMs continue with these analogies, with these existing analogies. So we see an ABM, for example, focusing on the spread of a so-called social contagion. And it continues with the analogy from epidemiology, taking an individual as susceptible, then infected, and then recovered. So in these ABMs, if there's an agent who comes into contact with another agent who carries this contagion or uses this product, then there's a probability that this agent will also adopt the product. And the model can never capture that real situation quite sufficiently, so more caveats are added. The product doesn't arise from a human-environment coupling, as Veblen and the other thinkers would have said. The product is just given. And the rules are modeled as if they are isolated binary situations, precisely so that they can be modeled by extending these existing analogies. So let's look at a more interesting example. This is called the hide and seek model. It does simulate, or it does model, the emergence of technology through a human environment coupling. But instead of using those systems that I spoke about in part one, or those mechanisms, it uses artificially intelligent agents to discover uses of these objects. So in effect, technologies emerge that can help these agents with their goal of hiding and seeking. Now, at first, agents discover some expected uses of these objects, and then they discover uses which makes no sense to us, but makes sense in their artificial environment. For example, one of the seekers discovered if he steps on a box in a certain way, the box would start moving. And this was a mistake in the simulation, but the agents exploited this like they would any other feature. So it allowed the seeker to surf on top of boxes over the barricades to find the hiders. And the hiders responded with defense strategies. So one small mistake in the model got amplified, and socio-technical evolution just went in its own way. So this proves that ABMs have limitations in modeling specific situations over time. Joan Robinson in 1980 showed us why you can't do that with equation-based models. And obviously in agent-based models, the problem is even bigger. And from Gibson's work in 1979, it is clear that artificial worlds would have their own affordances, exploitable by artificial agents, and that when you build more complex worlds like these, more opportunities for such mismatch will enter. And making agents smarter only makes the problem worse. All right. This has implications also for questions like whether AI would ever be able to understand us, but my thesis does not focus on that for now. Now, dumbing down these agents and oversimplifying the complexity in a system creates a different problem, as you'll see in the next ABM. So this is the alpha roll pub ABM. It assumes people act like calculators. In this model, each agent makes a yes-no choice of attending this alpha roll pub, the blue square. And the goal is for the agent to attend only if they think the pub is not overcrowded by their fellow agents. So if they think the pub is contains below 60 patrons. So how they do this is the model allows the agents to memorize past attendance figures for a couple of nights at the pub. And the model endows the agents with a couple of short equations that take these past attendance figures as inputs to predict the attendance of the current night. And based on this, the agent makes their choice. The agent is rewarded if they decide to attend, and the pub is indeed not overcrowded if they were right. And then the agent checks their little equations, which one brought it closest to the real attendance figure, and they'll use that equation in the next round. So the rounds go quite quickly. You can see in the ABM, it just flashes really quickly. So in a small isolated world like that, we might well make such decisions. But in the real world, as Gigerenzer explains. Gigerenzer is someone who advocates for Herbert Simon's original view of bounded rationality. He explains that more computation is not always best. Instead, effective decision heuristics emerges out of the structures inherent in our physical and cultural environment. Now, this model treats rationality more like a neoclassical economist's version, more like an optimization thing. It deals with risk in a small world, while the real world is full of uncertainty. And that's a point that Keynes also made. All right, so I analyze a couple more ABMs and I come to some conclusions. They can create complex models based on neoclassical assumptions. They can create artificial complexity, which is nothing like our economic systems. And they can easily explain complex physical systems. But complexity in economics is reduced through one of those three ways. So you get the artificial space in which the model is built. That combines with inappropriate analogies, and this is the problem. So what do we do? When building ABMs for economics, I want to distinguish between two purposes. The system-based models, these ones are abstract. They use an ABM strength as a concise and often visual explanation of a theory. Now, to illustrate this, these models include time, but they should not include real time. They should not include real or numerical values. Fine-grained models, these make it easy for policy analysts to plug in empirical data, run simulations, and make decisions. But these should be understood as point-in-time models. They cannot analyze a changing reality over time, as that hide-and-seek ABM tried to do. Now, my idea is for good system-based models to guide the development of fine-grained models. And to assist with these system-based models, the components and mechanisms from part one, from those eminent thinkers, need to be placed in analogical form. We need to make analogies based on that. So I'll show you two examples of these analogies. So we need something that can work with multiple products, and the product should be relatable to the agent's internal environment. So with this, an agent sees which one of these products can be used for one of its preferences. So imagine preferences, or imagine uses and preferences as these strings of letters. And an agent, the product an agent chooses depends on which one can satisfy its one of these internal strings best. So the agent chooses the best matching one. But this internal environment of the agent also needs to expand as the model runs. So to show you that, I want to talk about, yes, the internal environment needs to expand as the model runs. So let's talk about learning and collaboration. When two agents meet on the grid in an ABM at the same spot, it takes into account both agents' internal environments. So all of these strings. And each agent, so the two agents interact, each agent contributes something that the other agent does not know. So these two strings combine into a new string, something new, new information, or a new insight into the world. These become new strings in each agent and becomes a new product in the physical world. Now, in this way, this new product is a combination of two existing products. So why do I say that? Because those existing insights were not just insights or skills hanging in the air. They are defined in a physical situation somewhere in the world. Now, with analogies like these, we can build proper system-based models. And these models can help us to see where an ABM does not include the appropriate mechanisms for dealing with an economic system. So those are the three parts of my thesis. Thank you very much for listening.